Welcome to our talk on ICCV, Robust Unfolding Network for HDR Imaging with Modulo Cameras. Real-world scenes often exhibit a wide range of brightness, from shadows to highlights. However, standard cameras fail to capture the full range because of their limited responding range to irradiance. This leads to the underexposed or overexposed patterns in captured photos. High dynamic range imaging is a technique that expands the range of light captured in a digital image, which is widely used in photography, computer graphics, and etc. HDR techniques generally fall into three categories. Multi-exposure HDR, which captures images at different exposures and fuses them. Single-exposure HDR, which directly reconstructs the HDR image from a single LDR image. And the specific sensing technique that involves modifying camera hardware or employing specialized sensors to directly encode a wider dynamic range. For example, the neuromorphic, thermal, or modulo camera. Our work focuses on the HDR imaging using modulo camera. Modulo camera records the least significant bits of the irradiance signal. Specifically, when the accumulated count reaches predefined threshold, such as 256 for an 8-bit sensor, it resets to 0 and resumes counting. This periodic wrapping enables a theoretically unbounded dynamic range. The relationship between the HDR image and modulo measurement can be formulated as X equals the modulo version of Y, where X and Y represent the modulo wrapped measurement and the HDR image, respectively. The goal of modulo HDR is to recover Y from X. Research on HDR reconstruction using modulo cameras remains limited. MRF utilizes graph cut optimization with smoothness prior enforced. This handcrafted prior limits its performance on the real-world images with complex patterns. PNPUA iteratively solves a variational regularization model using a pre-trained denoising network as a regularizer. But its effectiveness depends on the domain shift between training and target images. Jagatap and Hegde proposed optimizing a TV-regularized variational model using an untrained decoder, where the HDR image is reparameterized and fit to the target by an untrained NN. However, this NN delivers inferior performance and incurs high computational cost due to per-sample training. UnModNet is a supervised end-to-end learning method, which casts modulo inversion as an iterative rollover classification problem solved by a black box neural model. While UnModNet offers faster inference compared to above methods, its generalization remains limited because it disregards the properties of the physical imaging process. Considering these limitations, we propose a deep unfolding network that explicitly encodes the modulo imaging process and its properties, enabling more accurate HDR reconstruction while maintaining computational efficiency. Our contributions are summarized as follows. We reformulated the HDR reconstruction with modulo cameras in gradient space by leveraging the IDO's continuity condition. We are also the first to develop a deep unfolding network for modulo HDR, which is derived from the variational model based on this reformulation, along with an auxiliary variable to effectively handle outliers. Besides, we introduced spiking neuron-based module to learn a sparsity-related prior for outliers, enhancing the performance. Our method shows superior performance over existing approaches on both synthetic and real datasets. We reformulated the modulo HDR in the gradient domain using our minor modifications of the 2D extended IDO's continuity condition. The resulted proposition 1 states that if the pixel's gradient in HDR image is less than half of A, the modulo wrapped gradient of a pixel in modulo image equals the one in the HDR image. This proposition allows direct modulo inversion in the gradient domain for pixels within this bound. For outliers, the property of their sparse structure can be exploited to identify and exclude their impact to reconstruction. Based on this reformulation, we defined an optimization problem as follows. The HDR image is iteratively solved by aligning it to the gradient information derived from the modulo measurement. We introduced an auxiliary variable V to mitigate the impact of outliers. The iterative scheme of subproblems using proximal accelerated gradient descent solver is unfolded, and the proximal steps for Y and V are replaced by 2 learnable submodules respectively. Sparsity regularization is enforced to V by the proposed spiking neuron-based modules. Each iteration is implemented as a phase block in the deep unfolding network as shown below. Our spiking neuron-based module is designed based on the leaky integrate N-fire model. The structure of this module is shown below. The spiking neuron aggregates outlier clues across unfolding phases, enhancing the model's ability to adaptively suppress sparse erroneous measurements and improve reconstruction accuracy. The outputs of all phases in the DUN are supervised using loss components that measure the pixel-wise difference in gradient space and the pixel-wise spatial alignment. Here are the performance and complexity results on the synthetic dataset. Our DUN achieves the highest performance with a lightweight design. Here presents the visual comparison on 2 Modulo samples of synthetic dataset, where our DUN provides the best visual quality. We also evaluated on the real RGB dataset. Our DUN yields the most authentic visual results for both samples. We performed ablation study as shown below. The left confirms the substantial contributions of our method's main components, while the right shows that the outliers are well identified by our spiking neuron-based awareness mechanism. In conclusion, we reformulated the HDR reconstruction with Modulo cameras as the direct inversion in gradient space for most pixels. We developed a deep unfolding network for Modulo HDR with an auxiliary variable to effectively handle outliers, as well as the spiking neuron-based modules to learn sparsity-related prior for outliers. Our future work will focus on enhancing the robustness mechanism against outliers and extending our DUN for other inverse problems involving Modulo operators. That's all. Thank you for attention.